Caberta. Oh, there we go. Okay, so yeah, all of this is work with Mark Piccatori. And the other sort of disclaimer I want to make is that this talk, Virginia, yeah, thank you. This talk sort of culminates to a statement, and unfortunately, the statement that it culminates to is not entirely proven. So I've written it as conjecture. There's some nice fun stuff along the way that is proven, so it's not all just like totally wishy-washy hypothetical stuff. But I wish I could say that the total punchline of the talk was there, but it's still sort of work in progress. So so if anybody has any ideas, please email me. All right. So disclaimers out of the way. Let me start the talk proper. Okay. So when maybe this counts as a disclaimer. Anytime I talk about a metric space in this talk, a metric space will always be some smooth manifold equipped with a Riemannian metric. So I don't want to be thinking about manifolds with non-Riemannian metrics. I don't want to be thinking about discrete spaces, anything like that. I'm only talking about smooth manifolds equipped with the Riemannian metric. So if I'm talking about a metric space and I don't say Riemannian metric, go ahead and fill that in your head. Okay. And we're primarily going to be interested in these sort of Riemannian manifolds that have an additional property, which is that they are homogeneous, which is to say that every point looks like every other point. Formally, that is that the isometry group of that space acts on it transitively, so it can take any point to any other point. So locally, it sort of looks exactly the same at every point. In this sort of classical question from the 60s and 70s, that everybody wanted to know was, can you categorize all negatively curved homogeneous Riemannian manifolds, also known as HMNs? And the reason this question was sort of interest is because people really like hyperbolic space, hyperbolic plane, and higher dimensional hyperbolic spaces. They have these really nice properties. Complex hyperbolic space, quaternionic hyperbolic space. These are all examples of these nice Riemannian manifolds that have this nice property of being negatively curved. They're homogeneous. They're, you know, these very nice things, but they are also symmetric spaces. And so really what this question says is, if you drop the requirement that you're looking at symmetric spaces, what else do you get? What else do you see in that universe? So that was the question that was a very, very big deal. This was answered by Heinze in 1974. So he said, okay, you do get some things beyond just symmetric spaces, but they don't look that different. So what he tells you is that every time you have a negatively curved homogeneous Riemannian manifold, which will herefore be called a Heinze space for this result, anytime you have such a space, it's isometric to a connected solvable Lie group equipped with some given left invariant metric. Okay. And furthermore, if you're looking at one which is contractible, if you're looking at one which is diffeomorphic to R to the n, then in fact you can give that a representation as a Lie algebra and equipped with some specified inner product. So essentially, if you've seen the solvable group model for symmetric spaces, basically what this theorem is stating is that that property goes through for all homogeneous negatively curved Riemannian manifolds. Okay, they all have a Lie group model where you can think of the space as a metrized Lie group. That Lie group acts transitively, simply transitively on the space. Okay, so a Heinze group then will be defined as any Lie group that admits a metric, a Riemannian metric of negative curvature. Okay, and of course, any left invariant metric on a Lie group obviously gives a homogeneous space. Why? Because the Lie group acts on itself by left translation. So to get from any point to any other point, you just multiply by the word in the Lie group that takes you from that group element to the other group element. So a left invariant metric on a Lie group is automatically homogeneous. Okay, so perhaps not surprising, but a very powerful theorem. Okay, and so notice I said solvable Lie group model for the symmetric spaces. Okay, it turns out for these spaces, the Lie group that you get is also solvable, and not only is it solvable, it comes with a very particular form. Okay, so if you have a Heinze group, you can always decompose it as n semi-direct R, okay, a one-dimensional R, for some particular nilpotent group n. And here's where we have sort of our first ambiguity. Okay, so if I start with a Heinz space, an HMN, okay, and I want to pick some Lie group that acts on it transitively, okay, i.e., pick some Lie group that admits a left invariant metric that makes it isometric to the Riemannian manifold that I started with, then actually there is some choice involved. There are some different expressions, okay? But what's not different about all of those expressions is the isomorphism type of the nilpotent Lie group, which is, I don't know if I use it in this talk, but we'll call the base group or the derived group, okay? So the base group will always be the same no matter which expression you find for the Lie group, which acts on it transitively. Really what's different, and obviously R is going to always be the same. So really what's different in that situation, if you have n semi-direct R and this semi-direct uses, I don't know, some automorphism injection psi 1, and you get that this equipped, let me get that a metric then. Okay, and you get, so this equipped with some metric, you get that that's isometric to the manifold, smooth manifold of interest that you begin with, and you get that it's also isometric to another Heinz group equipped with some, d prime different metric. All right. Again, what this statement tells you is that these n's are the same. Obviously, R is still R. So really what this is boiling down to is this map here. So in semi-direct product land, right, what does this side do? This side takes you from R and it takes you into, well, a priori doesn't have to be injective. And in our case, it will end up being injective, but a priori it just is a homomorphism from R into the automorphisms N. Okay. And what this statement is saying by Alexievsky is that you can always pick a representative of this isometry class that has the property that this is nice. Okay. Purely real is just referring to the generalized eigenvalues. I will get into what that means maybe in a little bit, but you can just say, okay, there's a particularly nice representative of this isometry class, essentially. Okay. So really then what this is boiling down to is it's boiling down to this automorphism here. Okay. Oh, maybe before I talk more about that automorphism, let me give you an example. So I said that this, oh, is that a question? I said that this class of spaces is a generalization of what happens in non-positively or negatively curved symmetric spaces, including the hyperbolic plane. So let's just look at that. So I always want to think, when I'm thinking of these Heinz spaces, I want to think of them in sort of an upper half space model. And the reason for that is that all of these Heinz spaces will have sort of this analogous upper half space model way of looking at them, but they don't have things like the disk model or the ball model. They're not symmetric enough that looking for a disk or a ball model will be successful. You really do want to only keep the upper half space model in mind. So let's go ahead and draw our upper half space model of the hyperbolic plane here. I'm going to label the point at the very top, the ideal point at the very top, infinity. Okay, and then here is the remainder of the boundary. So this is the boundary of H2 without infinity. Okay, so here's our boundary of hyperbolic space. And I want to think of the coordinates that I get by looking at it as an upper half space. So I kind of get these two R directions. Okay, so here's one R direction, and sort of here's another R direction. And I'm not talking metrically right now, I'm just talking topologically. And the reason I'm not talking metrically here is that this copy of R is exponentially distorted, of course. If I want to look for a, geodesics connecting points on this line, I'm going to go up and over, and I'm going to go more and more and more out. Okay, so this is definitely not geodesically embedded, But the green R is, okay? This is, in fact, a geodesically embedded copy of R. Okay, so geodesics connecting points on this green copy of R are, in fact, just lying on this R. All right, and so how does this relate to the solvable Lie group model that I was mentioning? Well, if you call this copy of R N, of course, R is a nilpotent Lie group. It's abelian. Okay, it's a very particularly nice copy of N. Then what we see is that H2 actually looks like this N, where again, this N is just this red copy of R, okay, semi-direct with this green copy of R. Again, equipped with some particular left invariant metric that that you get when you sort of look at the geometry of this space. All right, so so in this case, it is H2 looks like R semi-direct R, but when you get to higher rank symmetric spaces, in general, when I look at Hn, the Lie group that I'll see is some copy of Rn minus 1 semi-direct R. Okay, that's the solvable Lie group model. If I want to look at more complicated symmetric, negatively curved symmetric spaces, like complex hyperbolic space, looks like I apologize, I'm going to screw up the dimensions here, but you'll get some higher rank Heisenberg space, Heisenberg group, semi-direct with R. And again, what the complex hyperbolic space will look like then, if you use the upper half space model, is it will be foliated by copies of the Heisenberg group, which kind of shrink down as they get up, as they go up towards this ideal point at infinity. Okay, and in all of these spaces, there is this preferred sort of point at infinity, which is at the top of the upper half space model. Okay, so I'm trying to convince you that these groups that admit these actions on these negatively curved spaces are not sort of things that you've never thought of before. You've thought of them, just maybe not in this context. Okay. So what we want to do now is I now want to pass from these particular very nice symmetric spaces, and I want to talk about generic groups that can sort of look like this Heinze group thing. Okay. So Heinze group always has this form. And I want to talk about how we construct these Heinze groups more generally. Okay, so to do that, we need some algebra here. So we're trying to specify a particular kind of automorphism of N. So we would like machinery for describing automorphisms of a nilpotent Lie group. To do that, we'll start at the level of the Lie algebra. So a derivation of a Lie algebra is a linear endomorphism that respects the Lie bracket. So here you can just think of this condition as being respects, what's the word I'm trying to think of? Cooperates with? That's not it. So it's definitely a C. Well, I'll put respects. Respects the Lie bracket. Okay, so it's just a linear endomorphism that respects the Lie bracket. You could consider the endomorphism that just sends all vectors to 0. That's fine. This condition will become trivial. Notice that I am saying endomorphism. I'm not requiring it to be an automorphism. I am saying just really generally an endomorphism. Okay. And really, if you want to have the right sort of mental picture here, you want to kind of think of alpha here as a matrix, where sort of this is the dimension of this matrix is sort of the dimension of the Lie algebra here. Okay. So that's what a derivation is. Again, it's not an endomorphism. It's not an automorphism. It's an endomorphism. So how do we take an endomorphism and get an automorphism out? Is you exponentiate it. Okay. So a derivation is going to have a particular property. Remember that I said that these copies of R, or more generally a nilpotent Lie algebra or nilpotent Lie group, as we foliate upwards, remember that I said those are going to be exponentially distorted. So let's codify that shrinking behavior. Okay, we're going to call a derivation contracting if, well, when I exponentiate it, I do get an honest automorphism. And remember what I said. I said that you can think of, now if this is in, let me maybe write it like this. I can think of, when I exponentiate this, I can think of this in aught n, and in particular, I can think about it as a matrix, and I'm looking at a real valued, I'm looking at Lie groups over R, so I can really think about it as kind of this real valued matrix expression, okay? So that means that I can make sense of its eigenvalues, and contracting is exactly what you want it to mean. I mean that all the eigenvalues are less than 1. So I'm looking at, if you're talking about R2, I'm looking at a transformation that maybe does something like this. It sort of shrinks everything in towards the origin, okay? And it does that in all directions, okay? I don't care kind of how fast it's doing it, but I don't want it to leave anything in place. I really want it to, if I iterate it far enough, I can get as close to the origin as I want to. Okay, this is taking place in the vector space in the algebra, but you can imagine on the level of the Lie group, essentially what this is doing is it's bringing all group elements towards the identity. Okay. So here's a more formal definition of Heinze group, or really an alternate definition of Heinze group, but it turns out it's equivalent. Okay. If I have a group which is in semidirect R with one of these maps, then when I get a Heinze group is exactly when this psi here is defined by a contracting derivation. Okay, what I mean by defined by contracting derivation, well, there's this really kind of funny tower thing going on that confused me for a long time until I realized I was missing a step of it, is that, right, what is psi? Psi is a map from R to aught n, to aught Roman n, okay? Which means that if I look at psi of t, I actually get a particular automorphism of n, i.e. psi of t is a map from n to n, okay? And then if psi is a map from n to n, I can talk about the differential of that map, okay? So then these are smooth manifolds. I can talk about the differential. So I'm saying that I want psi of t for any t I want to in R, psi of t to be the unique automorphism that has the property that its differential is exactly e to the minus alpha t, where this is an automorphism of n. Okay, so that's a really rough and quick introduction to Heinze groups. Suffice it to say that once I've specified the automorphism of n, really all I need in order to determine the group structure of this Lie group is I need to tell you about this derivation. Okay. So that is going to be our starting place for defining these higher dimensional extensions. Okay, when I say extension, I'm thinking about n being extended by R here. So I want to define a new class of groups that are extending by higher rank abelian Lie groups. Okay. So let's do that now. Now I want n to be a nilpotent Lie group. And now, instead of just one derivation, I want to take some finite number of derivations. So derivations are, again, you can think about them as matrices, but in particular, derivations, this class of derivations is a vector space. So I can think of what it means for those derivations to be a linearly independent set. So take a linearly independent set of derivations. I'll mention in a little bit why that condition is there. But take some finite list of linearly independent derivations. Now I want to define a new group. Okay, and now I want to define my G, where I'm actually mapping, instead of R, I want to map a whole RK's worth of automorphisms here, like so. Okay, and how are we going to do it? Again, we're going to do it in this sort of way of looking at Heinze groups, where I just want to tell you where the differential is. So if I have a particular vector, right, in R to the K, T1 up through Tn, then in order to define that, I just need to tell you what its differential is, because again, this is a map from n to n. So if I can tell you what the differential is on the level of the algebras, then I've told you what the automorphism is. Okay, and what I want it to be is exactly sort of what you expect it to be. I want it to be the sum of the alpha ITIs. Okay, or you can think about this as alpha 1 T1 times e to the alpha 2 T2, etc. So I'm basically just kind of combining these in the way that you would need to combine them to make sure that this is a homomorphism. Okay, because for this to be a homomorphism, I need these things to commute, so I need to be sort of adding them at the level of the Lie algebra.
Do you need to assume that these derivations commute?
Yes, sorry.
In this RN action, RK action.
Right, yeah, because for exactly this reason, yeah, because you need this thing to be, you do, yeah. Mm-hmm. I suppose I should have put that down. Yeah, I'm thinking about a very particular class of derivations. Yeah, so they will need to, because you need to be able to make sense of that. But we're going to, we don't want to just look at any group like this the same way that we didn't want to look at just any Heinze group, because we wanted to make sure that we could get something out that was negatively curved. So you can imagine here, you could, if you were not being careful, you could end up with Sol, for example. You could look at R2 semi-direct R or something if you had the derivations. Well, yeah, let me not get too off on a tangent. Let me just say that we want this to be, we want at least one of these things to be contracting. Sort of without loss of generality, we'll assume just that the one that is contracting is labeled alpha 1. Okay, and we're going to call that a contracting group. Mark and I have gone back and forth on what we want to name this thing. It's gone through like 3 different names, but here we are. Okay. So, right, this is the first thing you should be thinking of is, well, this probably won't end up being negatively curved, because if it was, then you would know by Heinze, right, that this would also look like, have an expression like this if it was negatively curved. And for various reasons, you can see why that's not going to work. You can look at things like the derived subgroup or whatever and see that that's just not going to happen. But maybe the easier way to see that it's not going to work is that the fact that this factor is higher rank is going to give you a way to embed flats. And you can just see that this is not going to be strictly negatively curved, because you'll be able to embed flats in this abelian factor. So what's the next best thing? The next best thing is cat 0. Okay. So we're going to get out our big sledgehammer here. And what is our sledgehammer? Our sledgehammer is a theorem of Eisenkot and Wilson, also from the 70s, which says I can tell you exactly when a Lie algebra has an inner product on it that turns the Lie group into a Hadamard manifold. Okay, so it says, look at the Lie algebra, look only at the algebraic information about it. I mean, it's all a Lie algebra has, right? Look at the algebraic information about the Lie algebra, and if it satisfies conditions 1, 2, 3, 4, and 5, boom, you've got a cat 0. You've got a Lie group which admits a cat 0 left invariant Riemannian manifold, and you can just check it directly. So immediately from this, you can go through, okay, the only thing that's sort of not obvious here is the fact that you do need this contracting condition. If you actually go through the Eisenkot and Wilson paper, you can see where that condition will end up being used. But yeah, you can kind of go through and just sort of directly check that these contracting groups, as we define them, do admit cat 0 metrics. You can also prove it directly, which we did, but it's kind of silly when this amazing result exists that can tell you exactly when this happens. Okay, so these contracting groups, not hyperbolic, but are cat 0. So what does that mean? That means we get access to a whole bunch of geometric tools to study them. Okay. Let me give you a quick example of a contracting group which is not a Heinz group. This will also come from the world of symmetric spaces. So SL3R mod SO3, SL3R mod SO3R is a symmetric space. It is not negatively curved. It is non-positively curved. It does admit a Ketzler metric. It's a contractible symmetric space. And so let me just show you how to think of it as a contracting group. Okay, well, you say that you've got this Heisenberg factor here. You've got this r to the 3 here. Notice it's three-dimensional because here's your three real variables. And how does the action work? This automorphism work? Well, you send, right, if I'm thinking of psi, which sends R3 to aught of the Heisenberg group, then what do? Well, I say that psi of x, y, z. Okay, I need to tell you what that does. Oh, sorry, I have my variables wrong. I apologize. This is R2. I apologize. This is H. So now, if I want to tell you what a particular vector in R2 does, so say AB, well, it needs to act on something in the Heisenberg group like this, and it's equal to this guy down here. Okay, so this is defined slightly differently. I'm not defining this using differentials, it's just the standard symmetric space construction for this group. And to verify the contracting condition, consider when A and B are between 0 and 1, and you see what happens over here. Okay, what happens over here is that this starts shrinking to, right, as you consider, if you sort of iteratively apply this, right, as A and B go to 0, then this matrix goes to the identity. Okay, why does it go to the identity instead of to the 0 matrix? Well, because this is happening on the level of Lie groups. So as I go, you can imagine sort of the corresponding, as I go to 0 in the Lie algebra, I'm going to the identity group element in the Lie group. Okay, and so you can either think about it as A and B approaching 0, or you can pick some, like, I don't know, A equals 1/2 equals B, and then iteratively apply, you know, psi of 1/2, 1/2, and I can consider that to the T, right? And then that will tend towards an automorphism that brings things closer and closer to the identity. Okay, so again, this is sort of an out there construction of these groups, but they're not groups that you haven't thought of before. They're just groups, a generalization of groups that you thought of in a different context. Okay, so maybe another slight detour to history before this slide. There's this very, very important result about negatively curved symmetric spaces and higher rank symmetric spaces as well, which talks about when you can find that a quasi-isometry is close to an isometry. And the those results, those sort of classical results in this field very much rely on the structures of flats and how these flats in those spaces intersect. So the first thing, if we want to study the geometry of these groups when they're equipped with Riemannian and left invariant metrics, is going to be to see what the flats in these spaces look like. So here's the first proposition I have for you, is that when you take a contracting group of this form, I'm going to omit the derivation notation, but when you take a contracting group of this form, then in fact these cosets are always totally geodesic. Okay, and actually they foliate the whole space. So if I'm thinking about cosets, again, if you want to go back to just hyperbolic space, the cosets sort of look like this. I can imagine foliating all of H2 by these copies of R. So here's maybe XR, and here's YR, and this is IDR. Okay, and I can foliate all of H2 by these, and they're always geodesic. And this proposition, again, should convince you why these spaces are not hyperbolic, because they have these high dimensional flats in them. But why H2 can be hyperbolic, because they have, sure, they have these flats in them, but they're flats of dimension 1. So that's okay. Right. And then we get if we want to be more specific, if you force all derivations to be contracting derivations, then in fact you can say something even stronger. Okay, and what we can say is if you take all contracting derivations, then actually you don't get any higher flats, and furthermore, even better, you don't get any higher quasi flats. Okay, so if I have a quasi isometry of r to the k into my space, it actually has to sort of lie in one of these max flats here. The reason this sort of all derivation rule is here is because I could do something really silly where I could take R with one contracting derivation and sort of like the identity derivation and define a contracting group that way. And this sort of extra dimension of not doing anything can sort of bump you up to a higher flat. So you take R to the K, and then you also add in a direction where you're sort of not doing anything. It's sort of a silly reason, but what this does for you is it allows you to control it and sort of lets you look at slices, codimension 1 slices of this Lie group and get things that look like lower dimensional contracting groups within them. Okay, but this is going to be a particular subclass of group that we're interested in, is when all derivations are contracting, because then you get this really nice statement that you know what the maximal quasi-flats look like, and that just lets you do some good geometry. Okay. Remember earlier when I told you that you could take this, I know this slide has a lot of text on it. Ironically, it's one of the less important slides despite how much text it has. But remember when I told you with a Heinze group, you could replace this with a different automorphism structure here, where this had the property that it was nice, and we like that. Basically, you can do the same thing with contracting groups. Okay, I can replace up to the isometry class of the ambient manifold. Okay, I can replace this class of derivations with ones that are purely real. And so this kind of goes back to Shandong's question, which is, you know, you have to have some nice control over these derivations. And so a lot of the machinery that we write out is dedicated to saying that, you know, sort of without loss of generality, you can focus on derivations that have these sort of nice properties, which allows you to just do a lot more with the algebraic structure. So really all this proposition says is that you can replace this with a set of derivations alpha 1 through alpha n, where these correspond to automorphisms of the Lie algebra. Remember, they're not automorphisms until I exponentiate them because they start as endomorphisms, but they correspond to automorphisms of n with real eigenvalues, purely real eigenvalues. Okay, and that just, honestly, that just makes our life a lot simpler that we can do that, because we're not interested in the Lie group as an algebraic structure. At the end of the day, we're not interested in these things as cat-zero Riemannian manifolds. Okay, so we start with sort of a manifold that is isometric to a metrized contracting group, and then we say, but not that one, the good one. Let me go. Okay. So now I'm going to get to kind of the first thing that I advertise in my abstract, which is that you can classify when these things have geometric actions by discrete groups. There's not really a great reference for this, but everybody seems to know it. Personally, I think it follows most easily from work of Eberlein in '82, but you know, this is really just sort of a classical result, which is that if you have an irreducible just means I don't have any non-trivial splitting, isometric splitting of my space into product manifolds. If I have an irreducible homogeneous Hadamard cat-zero Riemannian metric manifold, then if it's not symmetric, it never covers a finite volume quotient. Okay, so from there you can kind of see why that means that I'm not going to be allowing too many geometric actions, because if you look at the quotient by a geometric action, you're going to get something that's, I mean, not only finite volume, but by definition is co-compact. So the only way you can get finite volume quotients of irreducible homogeneous Hadamard manifolds is if there are symmetric spaces. So then the corollary of that is the following. It's if you have a contracting group and you give it a left invariant cat zero Riemannian metric on it, then if the resulting object is not a symmetric space, then in fact that group with that left invariant metric does not admit a geometric action by a discrete group. Okay, so that's cool. I mean, I hope I've convinced you that that's cool. It's a Lie group, okay, with when it's equipped with this particular metric, does not look like a discrete group, right? And that's sort of not the average type of Lie group that we think about, right? If you think about an average nilpotent Lie group, okay, chances are good that it has some finitely generated nilpotent lattice in it or something. Like the majority of the nilpotent groups that I think of, for example, are like Malchev completions of finitely generated nilpotent groups. So those obviously admit geometric actions sort of by construction. So here we have a class of Lie groups that don't look like finitely generated groups. But there's this sort of, maybe unsatisfying thing. Okay, this is not a group theoretic property, right? Because this only holds when you pick a particular left invariant Katsura metric, right? Why do you have to do that? Why can't you say that this is a completely Lie theoretic property? And you can make this statement will be a little bit weaker, but we can make an entirely algebraic statement. So to inspire that, let me tell you what the analogous statement is for Heinze groups. So this follows from Eberlein here. If I have a negatively curved Riemannian manifold, it's certainly cat zero, okay, if it's contractible. And so if you apply the theorem from the other page to Heinze's work from 74, you get the following restriction. If you take a Heinze group, so for some G looks like N semi-direct R here, then based purely on the algebra of N, we can rule out finite volume quotients purely on the algebra of N, because the only way that it could have a finite volume quotient is if it looks like a symmetric space. Now, we're sort of playing fast and loose. I could have a metrized Heinze group that ends up being a symmetric space, even though it started with a different Lie group structure, but it turns out that doesn't happen. So there's a little bit you have to do to show this, but it's not that deep. Basically, it says, okay, look at the algebra of N, and then if it doesn't look like the derived group for a solvable Lie group model of a negatively curved symmetric space, then this is not a manifold that covers a finite volume quotient. And again, this is weaker because you could have one that where N is one of these things, but the automorphism turns it into a completely different space that doesn't admit a symmetric metric and therefore doesn't cover a finite volume quotient. But this is an entirely Lie theoretic statement. And in fact, not only is it entirely Lie theoretic, it sort of only depends on this in here. So that's kind of cool. So we want a statement like that for our contracting groups. We want an algebraic condition whereby we can say, okay, I don't care what metric you come up with to put on this manifold. Okay, it's never going to look like a discrete group. Okay, and so you can do that. Okay, take a higher rank contracting group. When I say higher rank, I just mean N semi-direct R to the K, and K has to be at least 2. Okay, so that's what higher rank will mean. And now what you can say is if G does not embed into the isometry group of a symmetric space, then whenever D is a left invariant cat zero metric on G. Now I'm not saying for a particular one, anytime ever you have a left invariant cat zero metric on G, that resulting Hadamard manifold does not cover a finite volume quotient, and then from there you can get to geometric action. And so why does this hold? Really, this just comes from the fact that the isometric action is left invariant. So if G doesn't sit as the subgroup of isom X for any X, then that means that this implies that GD can never look like X. Okay, for a symmetric group X, because if it did, well, remember that the left invariant condition on it says that the G action on X is isometric, and therefore G would be realized as a subgroup of the isometries. So this is a purely theoretic statement. Okay. So that's sort of the stronger statement that I want to make now. Now I want to get into, with the time I have left, get into the statements that are not quite finished, but that are the stronger and maybe more interesting statement than this. Let me check. Do I have 50 minutes or 60 minutes?
50 minutes with, 5 or 10 minutes for questions.
Great. Okay. So yeah, so I'll just kind of give you an idea of what's going on the quasi-action side of things. So there's this big paper by Eskin, Fisher, and White called Coarse Differentiation from 2006. And they were asking the question, a sort of vague, broad question, which is, when can you get solvable Lie groups that are or are not QI to Cayley-graphs of discrete groups? Okay. So you can sort of reformulate that by saying, well, when does a discrete group quasi-act? So this is sort of act by uniform quasi-isometries on your solvable Lie group. Sort of that. So that's sort of one of the inspiring questions for this whole project. And so they give an example of the solvable Lie group that is not QI to a Cayley-graph for a discrete group, and so does not get quasi-acted on geometrically by a discrete group. Notice that these groups are always solvable. You can, that's just an algebraic verification. These are, no matter how you form them, they are solvable. So here's what we would like to show. This is what we're sort of vying for. We want to say that basically this was the previous statement, was that a contracting group, which is not a symmetric space, if all the derivations are contracting, never is acted on geometrically by a discrete group. And we would just like to weaken that just ever so slightly to quasi-acted on. And anybody that's ever looked at something called the pointed sphere conjecture, I know Sean Tong has, knows that jump is much, much, much bigger than it seems at first glance. But nonetheless, this is the goal. To do this, we want to look at the boundary of these spaces. So the boundary of a cat zero space is just the class of geodesic rays, where you consider two rays equivalent if they say at Hausdorff distance from each other. You can give this set, so I've just described the set, you can give it two different topologies. You can give it a cone topology and a Tits topology. Turns out that the cone topology on the boundary of a contracting group is just a sphere. You can sort of imagine it, right? It's diffeomorphic. If I take n semidirect r to the k, this is diffeomorphic to just r to the k plus n, where n is the dimension of n. So it's maybe not super surprising. In fact, it shouldn't be surprising sort of at all that the cone topology of this guy just looks like a sphere of rank k plus n minus 1. Okay, so that's sort of the less interesting case. What's sort of more interesting for our purposes is the Tits topology. The Tits topology is described very well in a paper by Heber called Geometric Rank, et cetera, et cetera, et cetera. He does a lot of work in the spaces that look like this based on their Tits topology. But here's an example of it. So this is a group, a specific group where I look at R2, semidirect R2. This is sort of the simplest case that's not a Heinze group with two derivations alpha and beta. And what the Tits boundary will end up looking like is something like this, where you'll have a bunch of circles, and these circles are the boundary infinity of the cosets of this guy here. And they all get glued together along this special arc here. Okay. And so you might ask what happens in the higher dimensions. Do you get a higher dimensional disk? And the answer is yes. So we're calling this thing the norm disk, but basically, if you look at the boundary infinity and visual or Tits, I don't care, or cone or Tits, I don't care. If you look at the boundary of the cosets of these guys and you intersect all of them, then you get a disk of dimension k. Okay. Sorry, k minus 1. So if this were a three-dimensional example, you would get sort of this cap up here, and then you'd get a bunch of spheres like hanging off of this cap, where these are big. So it's very hard to draw once you get to higher dimensions. But this is what kind of gives you the hope that you can mine the boundary for some information about this group. For example, Haber. Oh, I guess it was 93. That doesn't. Maybe it was 93. But he says, okay, this special region, he calls it the spherical cap as opposed to the norm disk. But what he observes is that G acting by left translation actually always fixes this norm disk. Okay, so this maybe should remind you of the H2 case. If I look at the action of R semi-direct R on the hyperbolic plane, notice that's not all of isom H2. Isom H2 is much bigger. If I look at just this group acting on the upper half space model, then this actually fixes infinity. Okay, and all we're saying is that in this infinity should be thought of as half of a copy of S0. Okay, so it's the intersection of all of these copies of S0, because all these S0s are the boundary of these vertical R copies, but these are of course the same point, whereas these are different. So it's this generalization to a higher dimension of what happens in the boundary of negatively curved symmetric spaces, or more generally Heinz spaces, which is that the spheres of these abelian foliations intersect along a hemisphere, topologically a hemisphere of each of them. And that hemisphere is fixed by isometric actions. Okay, what we'd like is to say, right, that hemisphere is also fixed by quasi-isometries, again, which should feel very similar to the pointed sphere conjecture, which I won't talk about. But for higher, in terms of a hyperbolic space, yes, okay, the quasi-isometries effect on the boundary is a well-defined thing. It acts by quasi-symmetric homeomorphisms, et cetera, et cetera. But of course, in a generic cat zero space, I can't talk about exactly what happens to the boundary under a quasi-isometry because that's not well defined. So that's exactly the hang-up of proving the conjecture, because we can't sort of talk about the quasi-isometry's effect on the Tits boundary immediately. So in the 0 seconds I have left, let me just give you an idea of the strategy here. Last year, there was a paper by Kleiner and Lang called Higher Rank Hyperbolicity, where they do this very in-depth dive of what you can say about the effect on the boundary from a quasi-isometry on a cat zero space. So this statement is worded in terms of contracting groups. Obviously, their machinery is much more general, but the long and short of it is that you get a bijection of top dimensional cycles in the Tits boundary. So here I really do mean the Tits boundary, not the cone boundary. In the Tits boundary, you get a way to assign cycles to cycles in a way that sort of respects the quasi-isometry on the interior. And there's this density lemma that they show, and they say, okay, if you have a geometric quasi-action and you act on the boundary and with these cycles, or sorry, if you have a geometric isometric action, right, and you act on the boundary, then you get this sort of density behavior of what happens with respect to the cone topology. And if that were true for quasi-isometries, then it would give us what we wanted. So if we could replace this with a quasi-action, where's the word action? Group of isometries. If we could do a group of quasi-isometries, then we would win. The reason we would win is that the norm just can't move anywhere because it's unique topologically. In the Tits boundary, there's no other region of the Tits boundary that looks like it, because it's sort of unique in that way. So if we knew that a geometric quasi-action would have to move it off itself in order to become dense in the visual boundary, then that would be a contradiction. Okay. But so this is the real challenge to get at the statement we want to prove. Maybe I'll stop there.
Are there any questions? About Tits Boundary, you have those, you have a picture and they have those spheres.
Mm-hmm.
They should also have some discrete points, right?
Yeah, like you mean sort of as you imagine going out towards the limiting sort of, I don't know.
There's also some harmonic direction that should be give you discrete points in the Tits boundary.
Yeah, I mean the thing is that if you look at sort of going out, sort of the analog here is if I were to imagine sort of an upper half space model, right? So here's an upper half space model of something like this. If I imagine the direction that I want to give me sort of a hyperbolic direction, I would have to kind of go straight out, because if I went down, you know, I end up here and I end up in the boundary of a flat. But the problem is that this is not geodesic, or it's not even quasi-geodesic. So if I tried to go out towards what seems like it should be a point, say a point in the contracting boundary, because it's a Morse, you know, Morse geodesic. Well, it turns out that that's not even a quasi-geodesic ray, because that is exponentially distorted.
You mean this is the entire Tits boundary?
Yeah. So what happens? What Heber shows is that you can get the Tits boundary, so that there's a so let's say there's the Tits boundary of G. What Heber shows is that you can surject onto this by taking the boundary of your R to the K and sort of moving it around by n, and that this is actually a surjection. So everything that you can find in the Tits boundary is actually does appear in a sphere which represents the coset of one of the abelian factors.
You do have that. I mean, by your definition, contracting group. You have the one in one direction is contracting. That should gives you negative. You know, it's harmonic direction, and the harmonic direction are isolating the Tits boundary.
Right. So it's sort of like I'm trying to see if I've got anywhere to draw still, right? It's sort of like you've kind of got two choices, right? So here's one. Let's say this is like R squared, and I'm looking at a group that looks like n semidirect R squared. It's sort of like, okay, if I go in R squared, I end up at a point in the boundary of R squared, right? So the only way to find like a hyperbolic direction, yeah, will be to kind of go outside. So you go sort of outside R squared and you go sort of into this foliation, you know, here's n1 R squared, here's sort of n2 R squared, and sort of to go out in this direction. But eventually,
no, you can go start with a point here, but transversal to the R2. You want to lie in R2.
Yeah, so you sort of pick an entirely orthogonal direction. Yeah, and then what happens is that if I start off in that orthogonal direction, I actually have to fall down and end up in another coset. It's sort of, again, it's sort of analogous to what happens in H2. Okay, here I'm in, if I go transverse to this copy of R, which is sort of my lower dimensional analog of the abelian component, if I go entirely orthogonal to it, which is the way that I would hope to find a hyperbolic direction, well, if I look at the geodesic that has this as the initial tangent vector, even with the best intentions, it
okay.
and the S naught. So it ends up here, and this point is still in the boundary, right? This point is in the boundary of, this is some N1 hit R. This is still in the boundary of that coset.
So there are two other questions in the chat. Can you take a look?
Yeah, the definition of the Tits boundary. It's kind of a weird one. It's the Tits boundary is the boundary that comes from the Tits metric, and the Tits metric is the length metric associated to the angle metric. So the angle metric basically talks about if I've got 2 points in the boundary, here's A-1 and here's A-2, it talks about what the angles are of the possible geodesics between them, or the angle between the geodesic rays that form it. Okay, so this is sort of the angle between A-1 and A-2. And then you form an angle metric based on this number, which I think is like exponentiating it or something, or exponentiating its negative. And then the Tits metric is the induced length metric from this angle metric. It's not super intuitive, but like Jean-Dong is pointing out, the Tits boundary of H2 is just a whole bunch of isolated points. Because the Tits metric gives them a distance of infinity to each other. And so, yeah, so I agree. When we started looking at these groups, it really seemed like the Tits boundary should have isolated points, but the more we played around with it, we just, I don't know, it sort of wasn't the case. Because what we originally, our original strategy was to look at the contracting boundary, which would be kind of consisting of all of those isolated points, and see what the quasi-isometries do to the contracting boundary, because the quasi-isometries should act by homeomorphisms on the contracting boundary. But we didn't find any of those points. Yeah, absolutely. So the Lie algebra structure of with the derivations alpha and beta. Yeah, that's a great question. So this is, let me erase the rest of this. Yeah, it sort of seems like I've got a very particular group in mind, and I do. So what this is the group R semi-direct R squared with alpha and beta, and alpha and beta here are, alpha is going to be the group. You can actually just pick numbers, and beta is you can just pick. I like picking prime numbers, but they don't even have to be. And so these are in derivations of the Lie algebra, which is R2, but now I'm thinking of vectors. And so the way this is sort of related to the Riemannian metric is that if I had just started with R2 semi-direct R with alpha equal to 2, 2, then this actually gives me the metric R to the minus 2t dx squared plus e to the minus 2t dy squared plus dt squared, which is H2. So what we're doing here is I'm basically taking two hyperbolic planes, skewing the x and y directions a little bit, okay, so that it goes fast. Oh, hyperbolic three spaces, I apologize. Taking two hyperbolic three spaces, skewing the x and y directions a little bit, skewing them a little bit again in another way, and gluing those together in such a way that this space is now foliated by R2s, and I've got an R2 here that if I move off in this way, I look at kind of one distorted copy of H2, and if I move off in this direction, I have another sort of distorted copy of H2. So your Riemannian metric, so you get a Riemannian metric on this guy that looks like e to the minus 2 alpha minus 5 beta dx squared plus e to the minus 3 alpha, or actually not alpha and beta, I apologize, that should be like e to the minus 2, let me call it t minus 5 r not squared dx squared, that's where I want my squared, plus e to the minus 3t minus 7r dy squared plus dr squared plus dt squared. And that's where you see that from there you can kind of see why that Euclidean part is asymmetrically embedded. So that, yeah, this is the group. The R to the fourth with this Riemannian metric is the group that I have in mind for this slide. And yes, you're right. SL3R mod SO3R is a symmetric space. And a priori, when you define contracting group, nothing here is ruling out symmetric spaces, and you do in fact get symmetric spaces. So that's the reason, for example, that these where's the statement I want? That's the reason that this this result has to have the caveat: if you don't end up with a symmetric space, then blah 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 blah. Because yeah, a priori you could start and you could accidentally have chosen a Lie group that is that does act transitively on a symmetric space. So that's why we need this result, because yes, you can have symmetric spaces a priori.
Are there more questions? Well, if no further questions, let's thank the speaker.
Thank you.
Thank you, everybody.
Thank you very much for joining us.
I didn't mute everyone. I was worried if I mute the speaker then.
Oh yeah, no worries. It's not a problem. Yeah, I know what you mean, because it definitely seems like there should be a non-empty contracting boundary, and that's what we thought for a long time. It's kind of surprising to me anyway that there's not, and I thought that I was wrong, because I was like, oh, there should be hyperbolic directions here, but it really is.
Yeah.
Where's the?
So is that contained in paper by paper?
Yeah. Let me.
Okay, I find a paper.
Yeah. So it's called on the geometric rank of homogeneous.
Okay.
Bases of non-positive curvature. It was in Inventiones, which is cool.
Okay, I will find a paper. Yeah, that's interesting.
Yeah, surprising.
So because there's complete understanding of Tits boundary, then
here, let me see.
You can use that to understand a quasi-flat. So you also have result of quasi-flat.
Yeah.
Do you use that result? Do you use that structure of Tits boundary?
Let me remember how we proved this. Yeah, I think that was using the Tits boundary. I think a lot of this, I presented it in sort of an out of order way, because we definitely start using the Tits boundary like right away.
Right. I should have stopped recording.
Yeah. Right.
Okay.
Right.